Physics 2211, Lab 3, Satchel to Call. Introduction purpose. This is the black hole lab. This lab has two parts. One, analyze the star's motion to find the mass of a black hole. Two, find the initial velocity of a spaceship so it can successfully move around a black hole without getting sucked into it or crashing into a planet orbiting the black hole. The purpose of this lab is to use computational models to find data on objects in outer space. Note, there is no experimental component in this lab. Background knowledge. Newton's second law. The final velocity equals the initial velocity plus the net force over mass times delta t. Position update. The final position equals the initial position plus the average velocity times delta t. Gravitational force. The gravitational force equals negative the gravitational constant times mass 1 times mass 2 over the magnitude of the radius squared times r hat. Displacement, position final minus position initial equals the displacement. Perpendicular and parallel forces. So the net force equals the parallel component of the force plus the perpendicular component of the force, which is also equal to the rate of change of the momentum over time, parallel component, plus the rate of change of the perpendicular component of the momentum over time. And then these two formulas you can use to calculate the rate of change of the perpendicular component of the momentum over time and the parallel component of the momentum over time, respectively. Part 1 overview. Part 1 of the lab analyzes the position and velocity of the star while it orbits a black hole. Using this data, the model calculates the mass of the black hole. At various points during the orbit, the system is the star, the surroundings are the black hole in space. Part 2, a computational model simulates a spaceship trying to go around a black hole. By running the simulation multiple times, we can find the initial velocity of the spaceship in which it goes around the black hole successfully. This means it avoids crashing into the planet orbiting the black hole and does not get sucked into the black hole. The system is the spaceship and planet. The surroundings are the black hole in space. Brief overview of the results. The average mass of the black hole was 1.05 times 10 to the 34 power kg. The initial velocity of the spaceship was the vector negative 1.25 times 10 to the power 7, comma 7.75 times 10 to the power 6 meters per second. Part 1, these are my initial conditions. Everything is in SI units. Part 1, this is my while loop. In lines 162 and 163, I calculate the initial momentum and the final momentum. In lines 166 and 167, I calculate the change in velocity and the momentum. In lines 170, I calculate the rate of change of the star's momentum. In line 173, I set the star's momentum equal to the net force. In lines 176 to 177, I calculate the parallel rate of change of the star. In line 181, I set the parallel net force equal to the parallel rate of change of the star. In line 184, I subtract the parallel net force from the total net force to find the perpendicular rate of the change of star. The perpendicular rate of change of the star. In line 187, I set the difference of the to the perpendicular net force. In line 191, I used the gravitational force formula to find the mass of the black hole. In line 193, I add up all the masses together. In line 1208, I find the average mass of the black hole. Part 2, these are my initial conditions. Everything is in SI units. Part 2, in lines 74 to 80, I calculate the net force on the planet by using the gravitational force formula to find the force from the black hole to the planet and the force from the spaceship to the planet and adding those values together. In lines 82 to 88, I do a very similar process but for this time it's to find the net force on the spaceship. In lines 92 to 96, I update the position and velocity of the spaceship and the planet using the position update formula and Newton's second law. In lines 108 to 109, I check to see if the distance between the spaceship and the black hole is the shortest it has been during the while loop. If it is the shortest, I update what the shortest distance is. This results. Part 1, the average mass of the black hole was 1.05 times 10 to the 34 power kg at the final position of the star. This was the magnitude of the net force, the magnitude of the parallel component of the net force, and the magnitude of the perpendicular component of the net force. Results. Part 2, the initial velocity of the spaceship was the vector negative 1.25 times 10 to the 7th power, comma 7.75 times 10 to the 6th power meters per second. The shortest distance the spaceship was from the black hole is 3.47512 times 10 to the 9th power meters. Possible errors for part 1. Different masses were obtained at different positions, so it may not be completely accurate. This may be caused by the fact that I rounded the gravitational constant. Possible errors for part 2. Got the mass of the black hole from part 1. Used trial and error to obtain the initial velocity, and the time interval may have been too short. Additional questions. Part 1. The net force represents all of the forces acting on the object. Its parallel component represents the force's effect on speed, while its perpendicular component represents the force's effect in its direction. The rate of change of momentum is how much the velocity changes. Its parallel component represents how much the speed is changing, while its perpendicular component represents how much the direction is changing. Additional questions. Part 2. I was unfortunately unable to figure this out. I tried to find the velocity of the spaceship when the momentum of the spaceship is orthogonal, aka perpendicular, to the net force acting upon the spaceship. Conclusion. Part 1. The average mass of the black hole was 1.05 times 10 to the 34th power kgs. At the final position of the star, this was the magnitude of the net force, the magnitude of the parallel force, and the magnitude of the perpendicular force. Part 2. The initial velocity of the spaceship was the vector negative 1.25 times 10 to the 7th power, comma 7.75 times 10 to the 6th power meters per second. The shortest distance of the spaceship from the black hole was 3.47512 times 10 to the 9th power meters. Thank you.